So a little bit of admin before we start. So exercises 3, I've sent you all an email about, hopefully. So if you want to submit exercises 3 for me to kind of have a look at, then the deadline for you to hand that in is the 20th of December. I think I said lunchtime. If you email that to me, then I will have a look through it and give you some feedback. There's no obligation for you to hand that in. I will put the solutions kind of up online. But if you do want me to have a look at it, I'm happy to kind of like do so. There will be at least a lecture on Monday, next week as well. Okay, so last time we were kind of interested in talking about how we can sort of do regression models in survival analysis. So basically kind of when we measured quite a lot of variables for an individual that we might think affected their survival times. And we said that there were 2 ways that we were going to do that. An accelerated failure time model, which is a completely parametric model, and then also a proportional hazards model, which is what's called semi-parametric. So I thought I'd do a recap of an accelerated failure time model first. Okay, so for all of these things, we're going to choose an individual that we're going to call a baseline, and we're going to, for that person, we're going to say that their variables x are equal to 0. And then everyone else is going to be measured with respect to that particular kind of like baseline individual. So my baseline is basically when x is equal to 0. And for that, I'm going to choose a parametric family of distributions that's going to specify the failure time for that particular individual. So let's do a sort of an, and I'm going to say that individual T0 is the failure. So T0 is the failure time of that individual. So, and I'm going to call that T given x is equal to 0. And I'm going to specify that by some distribution that has a parameter theta in. Okay, and then for that individual, I'm going to be interested in working out S of t for x is equal to 0. So that's the probability that an individual with x is equal to 0 lasts longer than time t. Okay, so if I did an example, I might decide that I'm going to model the failure time of a baseline individual as exponential with rate lambda. Okay, so I've specified a parametric family for that particular kind of like baseline individual, and then in that case, the survivor function for that baseline individual would be e to the minus lambda t. Okay, so baseline individual, I have to kind of specify their distribution with some thetas in that are unknown. Then, if I have an individual who's not a baseline, and they have variables that I've measured little xi, then for that individual I'm going to try and speed up or slow down their time according to their variables. So I'm going to try and speed up or slow down their personal time. Okay? And specifically what I'm going to say is that for this individual who has variables little xi, the probability that they last longer than time t, I'm just going to call that the survivor function when you observe somebody with variables xi, is related to this survivor function by just saying, well, it's the probability that your baseline individual lasted longer than psi of x times t. So that's just the survivor function for my baseline individual at time psi of x times t. Let's try and make that a bit neater. Okay, so intuitively all I've done is I've basically said probability that an individual with variables x survives longer than time t is equal to the probability that my baseline individual survives longer than time psi times t. Okay, so this individual has their time sped up or slowed down relative to my baseline individual. And I'm going to choose this psi term to be e to the minus beta transpose x. Okay, so that was what we talked about kind of like last time, about how we could speed up or slow down individuals' personal times with a factor that would allow us to basically kind of have a regression model. And we could test whether individual things that we were interested in measuring affected somebody's survival time by saying, is that an important characteristic in terms of speeding up or slowing down their time? Okay, and we said we can fit all these models just using kind of our standard maximum likelihood. So we can write down the likelihood of observed data simply by adjusting my likelihood to take into account this speed up or slow down factor. Okay. So in the case that we're going to choose a baseline failure time distribution of an exponential distribution, this actually simplifies really quite a lot. So let's suppose, for example, now that we're going to choose an exponential distribution for my baseline. Okay, so I've chosen my baseline and exponential distribution. Then for an individual who now has variables x rather than 0, so i.e. the probability that an individual who has variables x lasts longer than time t, well, that's the probability that my baseline individual lasts longer than time psi of x times t. And my baseline individual is just my exponential with rate lambda. So, and I'm going to choose a value for psi of e to the minus beta transpose x. Okay, and then since if my baseline individual I'm going to assume has rate lambda, then this thing here works out to be e to the minus lambda 0, and then where instead of I had t, I'm just going to put this number in instead. So that's going to be e to the minus beta transpose x times t. Okay, so now if I do a little substitution, if I rewrite my lambda as being e to the minus beta naught, then this thing here becomes e to the minus beta naught times e to the minus beta transpose x times x. So that works out to be e to the minus e to the beta naught or minus plus beta transpose x times t. Okay, so basically I can just take my lambda naught up into an exponential if I rewrite it as e to the minus beta naught. Then, if I create a new lambda as a function of x, which is e to the minus beta naught plus beta 1 x1 plus beta 2 x2 plus beta p xp, then that's basically that term there. So that just becomes e to the minus lambda x times t. And this is just my survivor function of an exponential distribution with a rate parameter now lambda x. So in other words, if I choose an exponential distribution to be my baseline, then for an individual who I've now measured variables x, then they're still going to have an exponential distribution, but their rate is now going to be this lambda x term. Where lambda x is equal to e to the minus beta naught plus beta 1 x1 plus beta 2 x2 plus beta p xp. Okay, so all of my individuals are going to still have an exponential distribution, but they're going to have different rate distributions depending upon what variables you've observed for them all. Okay, so in particular, if I want to work out the expected survival time of somebody who's got variables x, then that is just 1 over their rate parameter. And I can use kind of things like that. Okay, and this is what, if you use R, R will give you basically these beta naught terms. If you do R and then fit an exponential distribution, R will give you beta naught, beta 1, beta 2, and then you will kind of plug them into this formula, and it will kind of tell you what a lambda x is, and you can work out expectations and things like that. So that's why when we did the when we did the analysis kind of functions before, we had to exponentiate things and then take 1 over those values. because it basically fitted this more complicated model and it gave you these beta naught terms. So we can see that in an example. Okay, so this is an example which takes some patients who have leukemia. So leukemia is a cancer of the blood. And what happens kind of with leukemia is as you get sicker, then your body releases a lot of white blood cells. And these white blood cells, in the case of leukemia, aren't particularly kind of like well developed, so they don't work very well. So white blood cells normally like attack things that make you ill. If you have leukemia, you have a lot of these white blood cell counts, lots of which don't work very well. So you get something that's a bit ill, you get surrounded by not working very well, white blood cell counts, and you can't fight off illnesses very well. So generally, the higher your white blood cell count, if you have leukemia, the sicker you are. So this is some data where we had, how many patients did we have? Sort of 18 or 17 patients who we kind of came into my study. We measured their white blood cell count when they came in, and then this is their survival time. So this is how long they survived after they came in to kind of be measured. Everybody here sadly died, and we saw everybody how long everybody, so there's no censoring, we saw exactly how long every single person kind of like failed. So that's the data there. Okay, and we're going to try and do a model that says, does white blood cell count affect your survival time? So you can sort of see that, or maybe it does. These people who've got high white blood cell counts die very quickly. These people who potentially have lower ones seem to kind of last longer. But we want to be able to test that statistically. So we aren't going to model the dependence on white blood cell count directly, okay, because we would expect we want kind of like a linear relationship in expected survival time and our variable. That doesn't look very linear. So what we're going to do instead is we're going to try and transform white blood cell count to log. Okay, and that looks like there's a more of a linear relationship between the observed survival times, there's no censoring, and log of the white blood cell count. Okay, so we're going to now try and test how does this white blood cell count affect expected survival time, and is it significant or not? So we have to create our survival object. So there's no censoring here, so we don't need to worry about the second argument of my survival object. And then basically we're just going to fit a accelerated failure time model where we're interested in modeling the survival times, and we're going to see whether do they depend upon the log white blood cell count, and we're going to choose a distribution that is exponential. Okay, so we're basically kind of like in this situation here. So we're going to assume a baseline individual has exponential with rate lambda 0, and an individual with white blood cell count, a particular kind of value, is going to have basically a different rate parameter, but still be exponential. We can look at what we get after we fit that particular model, and it gives us back a summary of saying what we tried to fit. So it said you're going to fit an accelerated failure time model where the baseline distribution is exponential. You think that the log white blood cell count might affect the survival time, and then it gives you some kind of estimates here as to how well it kind of like fits. In particular, it gives you two terms, an intercept term and a log white blood cell count term. They are basically beta naught and beta 1. So beta 1 goes with the log white blood cell count, and that is kind of like your intercept term. We can look at basically the p-value to see kind of, does this log white blood cell count look significant? Yes, it does. That's very small. And we can now kind of try and use these values to say, well, what does that actually mean for how long somebody might survive for a particular white blood cell count? Let's do that. Let's go back to the slides. Okay, so key bits are those two values, and what it's saying is that for an individual who has white blood cell count WBC, they're going to be exponentially failure time distributed still, but their rate is now going to depend upon what you've measured, and it's going to be e to the minus beta naught plus beta 1 x1. x1 here is the log white blood cell count. Beta naught is 7.8 and beta 1 is minus 0.889. Okay, so that's going to basically tell me how I could model the survival time for any individual when they come in with a white blood cell count. If I want to work out their expected survival time, that's just 1 over that individual's rate. So I'd plug in their white blood cell count into here, work out their lambda, work out 1 over it. If I, for example, had somebody with a white blood cell count of 54, I'd plug that in. So e to the beta naught plus beta 1 x1. And then I would take 1 over that number, 1 over that rate. And so I would think that somebody who came in with a log white blood cell count of 54 might last about 73 days. If somebody came in with a white blood cell count that was a lot higher, then they would last less long. Okay, does anyone have any questions about that? Okay, great. So you don't have to just choose an exponential distribution for an accelerated failure time model. You can choose kind of anything within sort of reason. R will give you slightly different outputs depending upon what other distribution you kind of like choose. If you choose a Weibull, then you get something similar to an exponential. It will kind of give you terms beta naught, beta 1 that you can kind of plug in sort of here to see how a Weibull distribution might change. Okay, but you'd have to have a look at the kind of user manual for R to work out exactly what it gives you for the different cases if you choose exponential, Weibull, log normal, all those kinds of things. Okay, so that was everything that I wanted to talk about for accelerated failure time models. I said I was going to also describe an alternative approach to try and include multiple variables into a survival analysis. And the second approach I wanted to talk about is called proportional hazards. Okay, so for accelerated failure time models, what we tried to do was modify the survivor function to speed up or slow down time. What we're going to do with proportional hazards instead is we're going to try and modify people's individual hazards. Okay, so if you remember, hazard was sort of the instantaneous risk of failing at time t, given that you'd survived up until the time just before time t. Okay, and we kind of drew some plots of what different people's hazards might look like in different situations. So proportional hazards is we are going to try and modify those instead to take account of my explanatory variables. Again, I'm going to choose some baseline hazard, so a hazard for a baseline individual, h naught of t, And then I'm going to say, well, an individual who now has exponential variables x, I'm going to modify the hazard for somebody with exponential variables x by taking the baseline hazard and multiplying it by something. Okay, we obviously kind of need this thing here to be equal to 1 if x is equal to 0. And again, we need it to be always kind of like something that's positive. So here, the multiplier that we might use that increases or decreases somebody's hazard relative to what their x is compared with the baseline individual, we're going to choose psi of x here to be e to the beta transpose x. So it's the other way round from accelerated failure time models. It's a bit confusing, but you need to remember that you need to make sure you remember. Okay, so we're going to try and fit a model that basically says the hazard of somebody at time t who has exponential variables x is the baseline individual's hazard at that time multiplied by something that is going to take account of the exponential variables. Okay, and the nice thing about proportional hazards is that actually you aren't going to have to specify the form of that baseline hazard. Okay, so it's called a semi-parametric approach because of that. Okay, so we're going to precisely model the dependence of the different covariates through the e to the beta transpose x term. Okay, but we're not going to have to specify the form of the baseline hazard, unlike we would have to have done for the accelerated failure time models where we need to specify everything for the baseline individual. What that means is we're not going to exactly work out the distribution of failure. So we're not going to be able to, because we're not going to specify the baseline hazard, so we're not going to be able to say things like exactly how long somebody will survive if they have a certain set of variables, but we are going to be able to say that somebody will survive longer or shorter dependent upon what their variables are. Okay, so it's particularly kind of useful where you want to know which variables make a difference and exactly to what extent, but you're not actually interested in modelling the survival time directly itself. And that's actually quite common that you would want to, you have that situation. Okay, so proportional hazards is going to be able to answer things like if you give somebody a treatment, then it will mean their hazard rate is half what the hazard rate was if they didn't get that treatment, or if somebody smokes, then their hazard is 3 times the hazard of somebody who doesn't smoke. But it can't say something like if you drink 3 glasses of red wine a night, then that'll go the wrong way around. If you drink 1 glass of red wine a night, then that increases your expected lifetime by 10 years. Or if you drink coffee, then that will shorten your life by 6 months. So it can't answer the last one, but it can answer the kind of like top sets of questions. This kind of piece of work is one of the most used pieces of work in the whole of the sort of medical sciences. It's got probably like hundreds of thousands of citations. Okay, so it's different with an accelerated failure time model because, as I said, you don't have to specify really the baseline distribution at all. Okay, you don't have to specify the hazard, you don't have to specify the baseline distribution. If you want to, you can specify the baseline hazard function. If you choose a baseline hazard which corresponds to either an exponential or a variable, then the model that you get is exactly the same as the accelerated failure time model. But the variable and the exponential are the only distributions where that works for. So if you choose an accelerated failure time model that's different and you specify the hazard and it's not one of those two, it'll be different from the accelerated failure time model. So that they really are two different approaches to trying to kind of like fit or investigate how variables affect survival. Oh. What have I done? Right. So how can we kind of like try and fit a proportional hazards model? Well, you might kind of initially think, well, let's try our standard likelihood approach. So our standard likelihood approach is collect all the data that we've got and then split it up into the contribution to the likelihood of the individuals who failed. So that's the density at time t for those individuals. And then the people who were censored, their contribution to the likelihood. Okay, so that's kind of what we've always done previously. And the problem with that is that if I try and kind of work that out, I get something that I can rewrite as this particular kind of thing down there at the bottom. Okay, so I can rewrite it as the hazard times a survivor function. Okay, but the problem with that is I haven't specified what the baseline hazard is going to be, and I don't want to specify what the baseline hazard is going to be. This thing here includes a baseline hazard term. Okay, so I'm going to be stuck using likelihood directly in that particular kind of like instance, unless I'm going to specify exactly what my baseline hazard is, and I don't want to have to do that. Okay, so I can't use standard likelihood. So instead what I'm going to try and do is I'm going to introduce something called partial likelihood, which is going to work in a very similar way and has been shown, that was the previous paper, that it has all the same properties as normal likelihood to try and fit these models. And the way partial likelihood works is really trying to work out the likelihood of the order in which individuals fail rather than their exact times at which they fail. Right. So this is the idea of partial likelihood. So if I'm not going to specify my baseline hazard, h0 of t, then actually the times that the individuals fail doesn't really give me any information whatsoever. Okay, and I'm not kind of particularly kind of like interested in it. So instead what I'm going to do is I'm going to try and write down a likelihood of me observing the individuals to fail in the order in which they actually did fail. So I'm going to try and introduce some notation that's going to help me to do that. So zeta j here, that's a random variable, and that's going to denote the jth person to fail, conditional on the failure time of the jth person to fail to be tj. Okay, so basically that's saying, well, zeta j is equal to zeta j is equal to 5. That means that the jth person to fail was individual 5. I'm going to condition, and then I'm going to condition on these failure times, and then what I've observed is a particular failure order. So I've observed that zeta 1 is equal to I1. So I've observed the first person to fail. Zeta 2 is equal to I2. So I know who was the second person to fail, and so on. And then what I'm going to do now is try and work out a likelihood, which is going to depend upon beta, so my multiplier, that says, well, what is the probability that I observed the failure order that I did do for a particular kind of like beta. Then with that, I'm going to try and maximize that likelihood instead of the likelihood on the previous page. And David Cox's kind of like huge breakthrough was that saying that if I work with this, then that works just like a standard likelihood, and I can kind of do all of the same things with it. So I was going to try and explain how we do this step by step in a way that will hopefully make a bit more sense than what's on that slide. Okay, so in general what's going to happen, so I'm going to assume there's no censoring at the start. So if I think about what's happened in my trial, everybody's come in, and at time 0, and then I've got some failure times that I've ordered. So the first time anybody failed was T1. The second time anybody failed was T2. And the jth time anybody failed was TJ. Up to the people kind of like failing at the end. Okay, I can have a little column that lists who the actual failed individual was. Okay, so at time T1, I'm going to say that the individual who failed is I1. Here, the individual who failed is the second person to fail, I2. Here, it's the jth person to fail. Here it's the n-1th, and there it's the I-nth. I've got some censoring indicator. Okay, in the case where I've got no censoring, all these are going to be 1s. So I can kind of ignore that for the sort of time being. And then for each individual, there are going to be some covariates. So I1, their covariates, I'm going to say is X1. So the first person to fail had a certain set of covariates. The second person to fail had a different set of covariates. The jth person to fail had a set of covariates xj, xn-1, and xn. Okay. And I can think about here what's called what we talked about before, which is a risk set. When we talked about Kaplan-Meier estimates. So the risk set here is the number of people who haven't failed yet, who are still potentially at risk. So they're not failed and they haven't been censored. And I'm going to have a model that the hazard at time t of somebody with covariates x is e to the beta transpose x times my baseline hazard. Okay, so that's kind of like my general setup. Right. So rather than work with the likelihood directly, what I'm going to try and work out is what's the probability that I saw the order of failure that I actually kind of like did observe. So when I've got no censoring, okay, then what I want to work out is the partial likelihood So that is, for a particular beta here, that's going to modify everybody's hazards. For a particular beta, what's the likelihood of seeing the order of failure that I did? So for a particular beta, what's the probability that the first person who failed was actually the first person that I observed fail, that the second person I'd observed fail was the second person that I actually observed fail, and that the last person I observed fail was actually the last person who failed in my study. And I'm going to condition on their actual failure times. So basically, I'm not really interested in kind of that bit there. Okay, I'm just interested in saying what's the probability that I observed the failure order that I did. And I can try and rewrite this by considering each failure in turn. So for this to happen, well, the first thing that needs to have happened is we need to have had the first failure to be the person we observed to fail. We're going to need to keep all of the conditional bits. Okay, so that needs to happen. Okay, and then we need the second person to fail to be equal to the second person we actually saw fail, conditional on this having happened and all of this. Okay, then what needs to happen next is we need to have the third person fail be correct. So we need to have the third person fail actually be the third person that we saw fail. We need to condition on this having happened and that having happened. So we need psi 1 and we need psi 2. And we need all these t's. Okay, and we can keep multiplying all these terms together until we're eventually at the probability that the last person to fail was the last person that we saw fail, conditional on the order of everything else beforehand being the same, and all those failure times. Okay, does that make sense to everybody as how I've got why this is kind of a sensible thing to work out and how I've kind of got from that order to splitting it up into the individual things with a conditioning? Okay, so that doesn't look like we've particularly made it any simpler. Okay, but if we could work out these individual probabilities, we'd be done. So what we need to work out is what is the probability that the jth person to fail is equal to any particular individual, conditional on the stuff that's gone on beforehand and all of the failure times. Okay, and this, despite not look initially as though it's going to be easy to work out, actually really is easy to work out. Okay, and you can think about this in the following way. So at time just before the jth person to fail, what I'm going to do is think about what my risk set is. So at time tj, so basically that's when this happened, then we have a risk set Rj, so the risk set at time tj, which is going to contain all the individuals who could still fail. Okay, so that's basically all of the individuals who could be I here. And then what I'm going to do is I'm going to pick at random one of those individuals from my risk set. So what's going to happen is I've now got somebody who is going to fail at this time. I've got a risk set, so it needs to be one of those people. And the probability that it's an individual person is proportional to what their hazard is going to be. So I'm going to pick one of my individuals in my risk set with a probability that is proportional to their hazard at that time. Okay, so basically the hazard is that instantaneous risk of failure. I know that there is a failure at that time. They're all going to have slightly different hazards. Somebody needs to fail. I just need to pick out of those people. So I can think about this basically as there being a big bag with people in. So each ball in my big bag is going to represent a person. The size of the ball is going to be proportional to their hazard, so their instantaneous risk of failure at that time. And I'm going to be more likely to pick a bigger ball.